Hello everyone, and thanks for joining us today for our webinar on boosting your Eurocode 7 geotechnical analysis and design with LimitState GEO. My name's Tom Pritchard, I'm Principal Engineer here at LimitState, and I'm joined today by Colin Smith, who is the LimitState GEO Product Manager and our main presenter for the session. The webinar is due to last around 30 minutes, and it includes a few minutes at the end for questions. You can post these at any time using the question functionality in the webinar interface. And for any questions that we don't actually get around to answering live, we will follow up in the next few days with a reply, so don't worry about that. We'll also be making a recording of the session available on our YouTube channel, details of which I'll mention at the end of the session. So, without further delay, I'd like to welcome Colin Smith, and I'll pass you over to him now.
Okay, well, thank you, Tom, and welcome everybody to this, our fourth LimitState webinar of 2021. So today we'll be looking at Eurocode 7. We'll take a brief overview of current factoring approaches and how to conceptualize these for LimitState GEO. We'll also take a brief look at what could arise in the next version of Eurocode 7 and how this relates to ultimate LimitState numerical analysis. So to this end, I'll be using the software directly to illustrate some of the points, but as it's a short presentation, the main aim is to give you a flavor of what the software can do, so there won't be time to get into the details of the software functionality. However, as Tom said, there'll be time at the end for questions. I'm also going to assume some prior knowledge of Eurocode 7 and also throw in a quick caveat. Any mention I make to the new version of the Eurocodes applies only to the current drafts, and of course these may be subject to change. So that's the kind of outline of what we're going to cover. I won't go through the contents list, we'll just crack on. So we'll start with just a brief background to the technology used in LimitState GEO, just to give you that framework. So LimitState GEO is based on limit analysis, which is a rigorous method of analysis based on plasticity theory. And the nice thing about it is the only assumptions that we have to make is that the soil behaves as an ideal plastic material, and we can use, for example, more Coulomb or Tresca yield surfaces, which are familiar to geotechnical engineers. And this has been used for many, many years in geotechnics, and the sort of examples that you see include Coulomb wedge analysis, slip circle analysis, and Rankine earth pressure analysis. There's a slight caveat on Rankine analysis you can see on the slide there. However, for hand calculations, traditionally it's only used for simple mechanisms, maybe 1, 2, or 3 wedges, or 1 slip circle. And that has now changed with the development of numerical methods, and particularly discontinuity layout optimization, which is the basis of the LimitState GEO software. And it's a systematic automated method of identifying the critical slip line pattern. I'll just quickly go through the steps in the process so you're familiar with that if you haven't come across that before. We start with here a simple example of a rectangular domain with a load at the top and supports to the left and the base. Unlike a finite element method, we populate the problem with nodes. Here we're using 12 nodes. And then we connect every node to every other node with a potential slip line. And then we use optimization, and we can use very efficient, powerful optimizers that are available these days to pick out the critical mechanism from that set of potential slip lines. And so that gives us the ability to transform our kind of analyses from what might be a 1 or 2 wedge type analysis to one that can involve multiple wedges, multiple slip lines, and give us a much higher degree of accuracy with our analysis. And this method has been verified against a wide range of benchmark solutions, and is flexible enough to cover a wide range of different problem types. So that's a brief background to the methodology. Now we kind of move on to the Eurocode side of things, and first of all we'll take a look at the ultimate limit state. So a brief recap on that. In the Eurocode, we're expected to assess both the ultimate limit state and the serviceability limit state. LimitState GEO is a it's a plastic analysis program, so it's focused on the ultimate limit state. And when we think about ultimate limit state analysis and design, we recognize that the ultimate limit state is a hypothetical state that should never arise in practice. Nothing we build should ever get anywhere near the ultimate limit state. And the idea of Eurocode 7 is to ensure the probability of this ultimate limit state occurring is extremely low. And we do that generally through the application of partial factors. Now, if we actually want to do an ultimate limit state analysis, we're trying to analyze something we designed that shouldn't collapse. So we have to drive the system to collapse artificially by some means. And we can do this implicitly or explicitly. In many conventional sort of hand calculations, the process is implicit. We don't sort of see it. But in a general numerical analysis, we have to do it explicitly. So the two ways that we can do that in the software are increasing a load. So in this particular example, we've got a load on the surface, and the question is, how much bigger do we need to increase that load to cause collapse? Or by what factor A does the load need to be increased to cause collapse? And the software will give us a solution, what we call the adequacy factor, which is that multiplier on the load. And the load can involve surface loads or self-weight. The other approach is to say, how much smaller does the strength of the soil need to be to cause collapse? Or by what factor F do we need to reduce the soil strength to cause collapse? And in this case, our factor or adequacy factor is on strength. So that's a little bit of background on how the limit state GEO addresses these particular problems. So what's important here in terms of Eurocode, we'll come to this in a little bit more detail in a moment, is that if the adequacy factor is bigger than 1, the system is stable because we've had to increase a load or decrease a strength to get it to collapse. If it's less than 1, then the system is unstable because the load is already too big and it has to be reduced, or the strength is too low and it needs to be increased. And if we've already applied partial factors from our Eurocode, then this adequacy factor gives us a kind of over-design factor on our system. But in terms of the Eurocode, as long as we're bigger than 1, then we can say our system is stable. So we'll do a little demonstration, and this will bring up the software. So that comes up. Yep. So this is the standard software window. We have a number of buttons down the left and the top, controlling geometry drawing and basic solving of the problem. What's called a Materials Explorer here on the left, and a key item is this property editor on the right. Anything we click on here, anything we click on in the problem, its properties appear here, and we can edit those. So what I'm going to do, just for speed, is to look at one of the built-in wizards. Now you can bring in any geometry of any problem into this software, but we've got some built-in wizards as well that just allow us to very quickly build a standard problem, which allows us to explore these kind of problem types with ease. So here is a problem. We've got a surface load acting on that, and we want to know what kind of what would the collapse mechanism look like. So I'm just going to click this solve button. As soon as we've got the geometry, we get the solution there. I can animate that. Gives us an idea of the problem deformation. And we get an adequacy factor down here of 20.473, which is quite high. And if I actually click on this load, I get a background as to what the analysis has done. So it's saying we've got a variable load acting on a boundary. If I click on the boundary, it actually highlights a boundary that's relevant. And what we've done in this model was define a characteristic load or action on that boundary of 5, and it was defined as a variable action. At the moment, we're not applying any partial factors. So what this adequacy factor of 20 means is that that value of 5 has to be multiplied by 20 to cause collapse. So essentially, we're saying for this the way this problem is set up and the soil properties, it's saying that the load on the surface has to go up to 100 kPa in order to collapse this wall. So it's obviously quite stable. It's very unlikely we're going to be able to achieve a load of 100 kPa on the wall. Now, we need to think carefully about how we're applying these adequacy factors. At the moment, we're only applying the adequacy factor to the surface load here. But I could also ask the software, well, how much heavier does this soil have to be to cause collapse in addition to the surface load? And I can click on this and change its properties to true. And the software will then tell me what I need to do to that combination. And I get a different failure mechanism here and an adequacy factor of 3. And if I click on that, you can see then that it's made that zone, it had to increase its weight, which was originally set as 20, 3 times bigger to 60, and the surface load to 15, and then that combination will get failure. But we've still got a number above 1, so we're still saying this system is stable. Now that's looking at factor load. Just to illustrate factor strength, I can just tweak that setting there. I don't need to do anything to the loads. It will just take the loads as fixed now. It will fix all the loads. It won't change any loads. It will just reduce the strength of the soil until we get collapse. It has to iterate a little bit to get there. We get a different mechanism, and here we get an adequacy on strength of 3. Similar to the other one, but it's actually a different numerical result. And if I click on the solution here, it's telling me that all the soil properties defined in this problem, I don't have time to describe all of them. They're all basically undrained strengths for this one. These were their initial settings. And to get the system to collapse, we've actually got to divide all those values by 3. So the main soil strength has to drop to 8 kPa, which is pretty weak, to get this thing, or 8 or 15 to get this thing to fail. So we've got quite a margin of safety there. So that's just the adequacy factor. We now go back to the slides. How does this relate to Eurocode 7? Well, Eurocode 7 approach to ultimate limit state analysis requires actions and resistances to be defined in the problem and to show that factored actions are less than factored resistances. And essentially, this is equivalent to showing the following in an ultimate limit state analysis, that the adequacy factor is bigger than 1. And that's all we need to do. And it has the added advantage of covering all possible failure modes, whereas in hand calculations, we typically only are addressing 1 or 2. So let's take a slightly deeper look at Eurocode 7. And this comes down to thinking about how we apply factors. Generally, we should be applying our factors either before or after our calculation model. So we can have what's called input factoring. We apply factors to our parameters, we run our numerical model, and then we assess the result. Or we run our model, apply factors to the results, and again, we assess our result. And there are some examples in the literature where you might see factoring carried out inside the calculation model. There are various theoretical objections to this. And of course, our calculation model can include standard closed form equations like bearing capacity equations, finite element analysis, a DLO analysis, a method of slices, Rankine earth pressure. Any of those are applicable calculation models. So let's look at one of the aspects in Eurocode, which is input factoring. And if we look at the table of Eurocode partial factors, I'm assuming prior knowledge of these, we can see that we have essentially 4 design approaches or combinations that are available to us in Eurocode 7. I've grayed out the ones that are less relevant. The ones that are left in white are essentially material factoring approaches. And if we look at the way the factors are applied, essentially these factors are generally applied before we do the analysis. So I'll just look at DA1, DC2 for the moment. We apply only a factor of 1.3 to a variable in favorable action. permanent unfavorable and favorable actions are left as they are. We factor the source strength, we do an analysis, and we do our assessment. So again, we'll just do a little demonstration of that. So we'll pull up the software again. And we've got our gravity wall wizard here. And what we can do in the software is we have this thing called the scenario manager. And before we were running it with unit partial factors, we can select the Eurocode7 design approach 1 combination 2. So you can see those factors appearing, 1.3 on variable and favorable loads, these particular factors on material strengths. And then when we run the analysis, we may get a somewhat different mechanism. Our adequacy factor has dropped from its previous value of 3 to 2, and this was running with an adequacy factor on strength. And if we click on these diagnostics, we can see that we start off with our characteristic strengths here. We then apply the factors in Eurocode to reduce those. These are being divided by 1.4, and then the software is saying on top of that, you've really got to half them again to get anywhere near collapse. So that value of 2 is bigger than 1. We've definitely complied with the Eurocode. And you'll note that we haven't specifically defined an action or resistance. Essentially, all kind of actions and resistances in the problem are simultaneously considered by the software. And we could have done the same on a factor load analysis. I run that, again, we get a value around about 2, and I look at that. You can see that in this case, the material properties are factored implicitly, but the actions here, the variable load has had its value multiplied by 1.3 to give us 6.5. The unit weight of the soil is permanent, so its design value stays as it is. But again, to get to collapse, these things have to be magnified up, and that gives us our additional margin of safety. So materials factoring approach is really straightforward for numerical methods. You apply the factors in advance, run the solution, and that works. And I say very straightforward. In this type of software, ultimate limit state software, in a finite element approach, you have to use strength reduction approaches. But in this approach, you just need to look at the adequacy factor and see that it's bigger than 1. So that covers MFA. We then switch back and take a look at what's called action effect factoring, EFA, which is essentially an output factoring with a little bit of input factoring on it. So what do I mean by that? Well, let's again look at this table of factors. What I'm going to focus on, well, let's look at column DA2 here. I haven't got time to consider this, but DA2 applies factors to actions and also applies factors to resistances. The challenge for numerical methods for DA2 type approaches where we have a factor and a resistance is that the resistance factor is going to be specific to a specific failure mechanism. So we have to analyze a very specific mechanism. Now we can do that with numerical methods, but we're not using the full power of a numerical method to try all possible failure mechanisms. We're having to force it to adopt a particular mechanism. So this kind of resistance factoring is very useful for hand calculations or closed form type solutions. But for general purpose numerical methods, it's not so useful. And the revised version of the Eurocode is to some extent trying to take this on board for users of numerical methods. But we're going to focus on the first column, where we apply factors to actions, and there are no factors applied to any resistances. Now you'll note I've changed one of the bottom rows from resistance to action effect. And an action effect in this type of analysis is assumed to be something, a force in a structural element generally that we calculate at the end of the analysis. So that might be a bending moment in a retaining wall. Now, one variant of this type of factoring that is being used with the current Eurocode and is going to be made much more clearer in the next version is what's called a star approach. And we'll just see how we get to that. So if we're adopting an input factoring approach here where we factor up actions before our analysis, if we divide those initial actions by 1.35 and then multiply our final output by 1.35, we will get broadly the same effect, although this is strictly only true for linear systems. And so the idea with the action effect factoring is that we essentially apply no input factors except for this 1.1 on variable and favorable actions. And then any action effect, like a bending moment at the end, we apply a 1.35. So let's look at an example to make that clear. So in a sheet pile wall, we are required to show that the factored bending moment, the action effect in the wall, is less than the factored plastic moment of resistance. Now the factor on the plastic moment of resistance could well be 1. So we're basically showing that 1.35 m, where the 1.35 is our action effect factor, is less than the plastic moment of resistance of the wall. So we need to solve the problem and then post-factor the results. Now, in software like LimitState GEO, it can be simpler to adopt a slightly different approach, which is to rewrite this equation that we want the moments in the wall to be less than MP over 1.35. And then we pre-factor MP by 1.35, and then we apply our calculation model. And if the adequacy factor is bigger than 1, then essentially it is showing that the original equation on the previous slide does apply. And by adopting this approach, in the ULS analysis, we allow plastic redistribution of stresses, and if that's something we want to do, then we would get a more efficient design. But I have to say, of course, that we do need to check serviceability limit state stress states, as in some scenarios, those could be larger than the ULS states. So let's just wrap up by looking at an example of this particular case. So here, I've got a wall model that I've already built. And what we've got is loose sand up here and dense sand down here and here. In the scenario manager, I've put in the EFA factors 1.1. Here, there are no factors for the output because it depends which part of the problem we're looking at to apply our action effect factor. Now we have a variable surcharge here, so that's going to get multiplied by 1.1, but the dead loads are factored just by 1. So if I solve that, I get a factor of 1.34, and I'm using a factor load approach. So what that's saying is that the surface load, and in this problem I've also set the weight behind the wall to have adequacy on it, they've got to be multiplied by 1.35 to cause collapse. And of course, this variable load has a Eurocode factor of 1.1 applied to it. Now, if we look at that analysis, we can look at the bending moments, and software provides a plot of bending moment at the ultimate limit state, and it's coming up with a maximum number of about 125 here. So we could just take that result and multiply by 1.35, we get a value of 170. We could say, well, if we design our wall with that strength, then we should comply with the code, and we would comply with the code. However, we must remember that in this particular analysis, the adequacy factor is not equal to 1, it's bigger than 1. So that means these bending moments correspond to a problem where the weight of the soil here and the surcharge are not as originally stated or are their design values, they're actually these bigger values. So that's going to lead to an artificially bigger moment. So we're on the safe side. So there are two solutions to this in the software. One is to reduce the wall strength. And if we look at it here, I click on the sheet pile, it's probably appear on the right here. This is the moment of resistance, 150. We could just progressively reduce that until we get an adequacy factor of 1. And then that would tell us that's the strength of soil, of the wall that we need to comply with the code. And we would then multiply that by 1.35 to get the actual required value for our final design. I won't do that now because of lack of time, but it turns out to be 85. And if we multiply that by 1.35, we get 115 as our required value. The alternative way, and that was covered in the slides, is to take the value here. And if we're saying that's the value we're happy with, I can divide that by 1.35. So I'm using this little calculator tool on the right. Divide by 1.35. Sorry, I've missed a divide there. So it puts in 111. And then I run my analysis. And if my adequacy factor is above 1, which it still is, then I can say that that value of 150 is then will comply with the code. And what you've seen here in the analysis, if I animate it, is that we've formed a plastic hinge here. We've redistributed the stresses plastically, but we won't get a ULS if we put in that value of 150 because our adequacy factor is bigger than 1.2 or bigger than 1 in this case. Okay, we're getting near to the end of the presentation period. We're just going to wrap up with a quick look at some of the key changes in the next version of Eurocode, at least in the draft. So you may or may not have looked at this, but in the new version, rather than just being one document, there are 3 documents: general rules, ground properties, geotechnical structures. There looks like there's going to be quite a few additional clauses and guidance for users of numerical modelers to make use of the code much clearer and hopefully much more simple for numerical modelers. We've got the introduction of what are called consequence classes that adjust the partial factors that you use depending on the consequence of failure. Much improved guidance on water pressure factoring. And a restructuring or enhanced clarity on partial factoring. Essentially, the core values have remained unchanged, but they're just being badged in a different way. And there are many more changes and inclusion of different types of problems, such as reinforced soil and rock mechanics. So just to look at the partial factors table, this is a sort of simplified summary of what we're looking at. The left-hand 2 columns are those methods that are amenable to numerical methods, and you'll see those are the 2 approaches we just covered in this webinar. The EFA and the MFA method. RFA remains as well as before, effectively the old DA2, and the new volume 3 of the Eurocode specifies the type of resistance factors you need to adopt for different geotechnical structures. But they've got rid of the labeling of design approach and design combination. We now have design case, DC, and material factor type sets, material factoring sets that we put in there. But looks like some of this terminology, effect factoring and materials factoring, is going to come into that approach. Okay, that has pretty well got me there on time. Just quickly run through the summary. Hopefully you've seen Eurocode7 methodologies built into the software. You can solve any ultimate limit state problem type. Very interactive. We can use the scenario manager to switch between different partial factor sets. and you can also use it, I didn't illustrate it, to switch between long-term and short-term analysis. In terms of Eurocode, material factoring is the most straightforward. Action effect factoring can be implemented relatively straightforward, but requires a little bit more attention. And in terms of looking at the new Eurocode, it's been expanded to address a wider range of issues and improve clarity for numerical modelers. So I will wrap up there. So apologies, we've just hit the end of the period, but if there are any questions, I will attempt to answer those. So let me just see if I can. Sorry, I'm just trying. Okay, so in the question, I had a question about this problem, but not that particular example. Let me just bring up the. The question was essentially, if the mechanism connects with the boundary here, is that an issue? And the answer is yes, that might be constraining it. It's like having a piece of rock in place here. So you can grab the boundary and pull it out. I'm doing this quite crudely here, but you can stretch it out a bit, and the mechanism should then sort of stay within the problem boundaries. I've obviously modified the slope a bit there by stretching it the way I did, and we can see here, in fact, that if I make the soil body deeper, the mechanism does get larger, so one would have to adjust the setup in that particular case. Okay, in view of the time, I will pass back to Tom just to wrap up. So thank you for listening, and hope you found that useful. Yeah, Tom, if you want to wrap up for us.
Yep, thanks Colin, and thanks to everybody who attended today. We obviously hope that you found the webinar informative, and as I said at the start, we'll be following up on any questions that have come in subsequently in the forthcoming days, as well as uploading a recording of this session to our YouTube channel. For more information on LimitState GEO, you can visit our website, send us an email, or follow us on social media, so LinkedIn and Twitter. If you just search for LimitState on any of those, then you should be able to find us. Finally, please do look out for our other webinars that deal with LimitState GEO and our other software, which will be happening later in the year. We'll be sending out event notifications by email in advance of these, as well as advertising them, like I say, on our social media channels and also on our website. So finally, thank you all for listening, and I hope that you can join us again for one of those future sessions. Goodbye.